Hi, y'all. So I'm just going to go over the group work. I'm just going to do the few questions that we didn't get to at the end of class. So I'll start here with question 14. So when we're asking about something being, it asks which of these cases is the arrow not indicate the chief position of nitration. So we need to tell if these are ortho-para-directors, and if there's two, we need to see if they're both directing to the same place, or if the dominant one is the one that's directing that we're going to actually see. So in this case, this would be an ortho-para-director, and so would this. This one's stronger, so I'm going to put a star by it. So this is going to go either ortho, here, or para. There's already something para, so ortho is the only position. Now this is also ortho-para, and because it's in this position, that means it would go here or here. But because this is a more strongly ortho-para directing, strongly activating, this would be the preferred position. So I agree with that. That's a check mark. This is an electron withdrawing group. So this is meta-directing. This is an electron withdrawing group, also meta-directing. So this position is meta to both of these. So I agree. That's where it would go. This one, I feel like they're both ortho-para, so here or here for the first one, here or here for the second one. So these are all equally directed to any position. So I don't agree that this would be the main place. I think it could kind of go anywhere there. This would not be the major one. This is ortho-para directing, so here or here, ortho-para. This is also ortho-para directing, but it's weaker. This is more strongly, so it would dominate. So again, because this is the dominating side, I agree there. This is meta-directing, and this is ortho-para directing, and this position is meta to your meta-directing and ortho to your ortho-para directing, so I agree it would go there. So this is the only one that there's not a clear position it directs to, and that all of those would be equally favored. So I can't argue for one position over the other, so I don't think that we can say this particular position would be favored. So that's why I can't go with question 3 being there would not be any substituent going there. And I do want to point out, it asks the chief position of nitration. It doesn't matter what is happening. These will direct to the same place. Like no matter what, if you have nitration, bromination, it doesn't matter what's being added. It only matters what already exists on the ring for us to see where the substitution happens. Okay. Oh, this is the one where I already worked it out. Let me switch papers real quick. Okay, so very similar to what I did at the beginning of the chapter 15 practice problems, when we talk about why some things are ortho-para or meta-directing. This question asks which one of these is going to get substituted, right? So does it attack carbon 2 or 3? And the way I would do this is I'm going to draw out the reaction. And I'm going to draw, it's not the uranium ion on here, just this carbocation. So E+, we're going to have it go to position 2. If it goes to position 2, the positive charge is here, plus the hydrogen. And now we're going to look at resonance structures. So first, this double bond could come in and fill in at this positive position. And you get the double bond here and your positive charge here. That should go all the way. E and H. And then this lone pair can come in. And the positive charge will move here. And you still have your H and your E. Okay, so that is 3 resonance structures where the carbocation is spread around the ring. In this one, if we go to carbon 3, it attacks the E+, So the E goes on carbon 3. Well, that should be an E with an H here. And then this is the positive charge. This lone pair could come in and fill in on this resonance structure here. E. And this would be positive, and then you'd have a double bond over here. So these are the only two resonance structures I see. I guess it would be possible technically for this to come and fill in, but the ring strain for two double bonds here like this, I think would be kind of insane. I've never seen a structure like this before. I don't think that this would exist, or if it did, it would be a very, very small contributor. So this is telling me that there's only two resonance structures if it goes to carbon 3, but there's 3 resonance structures if it goes to carbon 2. So carbon 2 is the preferential place for substitution. So this is very similar to when we're trying to tell if something is orthopara versus meta-directing. We're going to go through that same process where we go ahead and do the substitution and see where the carbocation is, and that's how things either become orthopara versus meta. This is the same idea, but just on a different type of ring. Okay, and then for question 16, predict the intermediates and final product of the following reaction sequence. This seems long and intimidating, but this is only things that you've seen before. So the first one, the aromatic ring with Br2 and FeBr2, that should be FeBr3, is just a bromination. So you've seen that several times. I did have someone talk to me about how they were struggling with bromination. Like there's several different bromination reactions that we've learned. So I just want to remind you, if you have Br2 and CCl4, that's an addition reaction. It adds 2 bromines. If you have Br2 and H2O, that's a halohydrin formation. It'll add a bromine on one side and alcohol on the other, but it's also addition. So this is chapter 8. Chapter 8, if you have bromine with H nu or heat, that's chapter 10. That's a radical reaction. And then bromine with FeCl3, FeBr2, any Lewis acid, that's an aromatic reaction. So hopefully you remember, you can kind of go through those and not get too mixed up with that. So the first step is bromination. And then when we have a bromine with magnesium, that's a Grignard reagent. So this is the product after step 1. This is the product after step 2. I usually go ahead and just redraw my Grignards like this. That's just easier for me to do. And that's going to react with this epoxide, and it's symmetrical, so we don't care which side it attacks. Either way, it'll be the same. And so this is carbon 1, carbon 2, and the oxygen. So the bond forms between this benzene and carbon 1, and then carbon 2 has the oxygen bonded to it. So the bond forms here, this breaks, and you get an O minus because there's 3 lone pairs around it now. So that's the product after it reacts with 3, and then H3O plus will just turn this into OH. 1, 2, okay, and then now we react with PBr3. So hopefully you remember what PBr3 does. Similar to SOCl2, PBr3 just turns alcohol, primary, secondary alcohol, into a bromine. SOCl2 would turn it into a chlorine. So this is after step 4, this is after 5, and then Mg again. So that, I didn't actually draw it out, turns it into a bromine. Then with Mg with that bromine is actually just another Grignard reagent forming, so MgBr. And I will always go ahead, just so I don't lose track, turn this into this. So we have carbon 1, carbon 2, and carbon 2 has the carbanion on it. And it's going to attack, always if you have a nucleophile with a carbonyl carbon, as long as there's not an acid-base reaction that happens first, it's going to attack there and kick up. So we get O minus from this, and then on this side we have a bond between carbon 1 and this. So that's carbon 1, carbon 2, and 3 is where the benzene ring is. And then, so that's after we react with 7. And then the next thing is just acid, so that just turns this into an alcohol. So you have a 6-membered ring with a carbon chain and a benzene off of it and an alcohol. So I think if you have a question like this on your exam, you want to go through and have the mechanism for each step. Make sure you number your carbons so you're not losing carbons, and that you know what each of these reagents do. Okay, consider the oxygen atom and the molecules of furan and tetrahydrofuran. Furan exhibits aromatic properties, so that's this one. THF, tetrahydrofuran, is not aromatic. So compare the hybridization of the oxygen, the lone pair in each of these species. So the first thing I'm going to do is say this oxygen has 1, 2, 3, 4 electron domains off of it, or 4 things bonded to it. So this is going to be happiest if it's sp3 hybridized. All 4 of these, this bond, this lone pair, and this lone pair, are all going to be in the sp3 hybrid tetrahedral shape. And that goes all the way back to like Gen Chem, when you did this with water, and water had these 2 lone pairs. It's in the tetrahedral shape for Vesper theory. Tetrahedral shape, but these 2 aren't there. That's why water is bent. So this is sp hybridized, just sp3 hybridized exactly the same way as water. So that's that. But then over here, you actually get a hint because it tells you that this is aromatic. So if it's aromatic, you know there must be a ring of p orbitals all the way around. So there's a ring of p orbitals all the way around, and there has to be 6 electrons in them. So 2 come from this bond, 2 come from this bond, and there could be 2 from one lone pair. So if there's p orbitals all the way around, then the rest of these are sp2 hybridized, including this oxygen, which means in that sp2 hybrid orbital is that lone pair. So this oxygen is sp2 hybridized to allow the lone pair to go into the p orbital, so it can be aromatic, where this one is sp3 hybridized, because if you don't have aromaticity, the next best thing is a hybrid orbital. Okay, I hope that's helpful for you. We did go over the rest of these questions in class, and then I believe Dr. Corrales is also going to be posting a key. Good luck studying.